We have the basic parameters we need to understand a membrane voltage, right? This resting membrane potential. I am going to do a little thought experiment here, and let's give ourselves a semi-permeable membrane here. And this is going to run around, entirely separate the speaker into two parts. So it goes along the bottom, and I'm not trying to do a three-dimensional diagram here. Just realize it's a perfect membrane. We've got it so that it's sealing up perfectly around the edge. No ions are going to get around this. So now that we have a semi-permeable membrane, we can make up a solution on either side of this. So let's imagine, here over on the left side, we're going to take about 100 millimolar potassium chloride. We're going to put that in there. We're going to put a little salt in there too. Let's do 10 millimolar just sodium chloride. And let's flip that for this side. So this is going to go into the left here. Over on the right, let's just use 10 millimolar potassium chloride and 100 millimolar sodium chloride. And that's going to go in on this side. And well, let's make this membrane permeable. I want to say it's only permeable let's make it to potassium. So only potassium can move through here. Chloride, you're out of luck. Sodium, the same story. So if we did look at this, we have way more sodium over here on the right side than the left. It would try to go down its concentration gradient, right? But it would hit the membrane, boing. Sorry, sodium. Now, potassium, on the other hand, can pass through, and we do have a nice concentration gradient for potassium. So potassium over here, some of it is going to go down its concentration gradient. I made the arrow go down. Now, imagine we had our voltmeter set up while this was going on. Let's see if we've got a charge across this membrane. Well, this positive charge that moved over to this side, yeah, we're making the right is more positive. And as a consequence, well, the left is more negative. Let's see if we have this voltmeter set up over here. Okay, we can treat the left-hand side just to keep this the same way as inside. So let's put a recording electrode down in here. So we'll say this is recording. I'm just going to abbreviate it. We'll go put another electrode on this side. This is going to be our reference. And of course that would feed into a little voltmeter. And I've done the math on this, and I can even tell you what we're going to record in here. So look at what we're doing first. This is recording compared to the other side. Positive charge left the left-hand side and went over to the right-hand side. So you can predict already that the left will be negative compared to the right. And that's exactly what we see. And matter of fact, I can even tell you it's going to be about minus 61.5 millivolts. And I'll show you how I did that little calculation here in a moment. Now, one of the things that you're probably thinking is, well, what do these concentrations look like? And if we didn't have charges, well, this potassium chloride, we would reach chemical equilibrium across this membrane, right? That's just the same type of equilibrium you learned about in your introductory courses. But think about this. So concentration gradient another way we describe this concentration gradient is a chemical gradient. So the concentration gradient is certainly a driving force for potassium, but because we have this charge on here, we also have to think about an electrical gradient. And we can see from a voltmeter there that this side is negative compared to this side over here. And as a matter of fact, these charges tend to line up right along the membrane. So we have a lot of negative charge right here and a lot of positive charge over on the other side here. And that's just because opposite charges are attracted to each other. So these sodiums, again, can't get through the membrane, but because there's an electrical field, the left is more negative, these sodiums are going to line up here. And potassiums from this side too. So any charged, positively charged particle is going to be lining up with the membrane. Our chloride up here, the negative charge, it's going to be pushed away. So that chloride will be hiding way over here. So like charges repel each other, opposite charges are attracted to one another. That's our electrical gradient here. So if you think about this, all right, so we have a strong chemical gradient or concentration gradient driving potassium across the membrane here, but as the inside becomes more negative, well, that positive charge associated with that ion is going to be attracted to the negative charge. So that's going to limit how much potassium crosses the membrane here. And we will reach a form of equilibrium. It's just not only chemical equilibrium. We're going to be reaching electrochemical. So this happens when the electrical forces are equal and opposite to the chemical forces or the concentration gradient. And that is going to determine just how much of this substance can move across the membrane. And it's a little complicated, but we can do the math on this and figure out how many moles of potassium moved across the membrane to produce this charge. And I'm going to spare you the details of that because we have to understand membrane capacitance and things like that. But I can tell you how much crossed, how much potassium went across. We got about and this is per unit space on the membrane too, and this is per centimeter squared of that membrane. That is a tiny amount of ions moving across the membrane to produce a fairly large change in charge, and that we see in biological systems as well. Doing the math on the biological systems, so this is the beaker. So we get that 6 times 10 to the minus third moles per unit area. If we took a little segment of axon, so I could say an axon, and we produce the same type of charge differential here, the number of ions that would have to move across the membrane, it's about 1 in 40,000. That's a tiny quantity. As a matter of fact, that's on the order of, whoa, what is it? We could do the math on that. It looks like it's about, we'll do it as a percentage. So a tiny fraction of those ions moved across the membrane to produce a 61.5 millivolt charge differential. The point I'm trying to make here, don't memorize these numbers. The point is a tiny amount of ion moving across the membrane can produce a fairly large change in membrane voltage. And that's really how these resting membrane potentials are generated. And when we get to action potentials, you probably heard, oh, sodium comes rushing in or flooding in. Well, that's really just not true. Ions move across the membrane, but not very many. And that's why it's easy to maintain these gradients with just some simple transporters to maintain that. If we had a large amount of ion moving across the membrane, we would disrupt this resting membrane potential fairly quickly. So, okay, point being, very few ions are needed to produce this change in membrane voltage. And there's a way to calculate those changes in membrane voltage. Let me go back up here because we're talking about the ions moving across the membrane. So what's our new concentrations that we have up here? They're exactly the same. Well, exactly is an exaggeration. So instead of 100 millimolar, maybe we have 99.99999999999 millimolar. It's really so small of a change in concentration that we really can't detect it. So again, it's a little like, as Dr. Siller likes to say, taking a thimble of water out of the ocean. Yeah, technically you reduce the volume, but it's completely insignificant. So let me show you some of the math here. I know I've just got some constants here, but I want to show you a formula so that you can begin to understand what's going on with this ion movement. There was a physiologist, well, actually he was a chemist named Walther Nernst, who derived this formula that I'm going to show you. And he actually was involved in developing some of the components of the laws of thermodynamics, and he got a Nobel Prize for this in 1920 in chemistry. So let me show you his formula, and it's just, let's do it fairly large so you can see it here. Voltage at a point where we're going to reach this equilibrium, this electrochemical equilibrium before, and we're going to do biologic systems, so I'm going to add ion down here. So the E stands for equilibrium, and ion just means ion. Okay, so let's see what we've got here. This is going to be equal to divided by, this is going to be a negative number because of the way we do these things. Okay, we're going to have to multiply this times something. Let me change the color here. It's natural log times the ion concentration. This is our concentration gradient here. And this is going to be across a cell membrane. We usually do inside compared to the outside. There are other ways of doing this. I can show you how to do it if you want. Now, let's look at some of these constants here. So the voltage across the membrane when we reach electrochemical equilibrium is equal to the gas constant times absolute temperature, so this is in degrees Kelvin, divided by this little z here. That's just the valence, or the charge on the ion. We're primarily interested in sodium, potassium, and chloride. So for sodium and potassium, this is just +1. For chloride, it would be -1. So it's actually easier than you might think. And this is going to be multiplied by Faraday's constant here. Let's see, it's a voltgram, or we could say coulombs. But that doesn't really matter too much. I don't want to go too crazy with this because I'm just trying to prove one little point here. So Z is electrical, and everything else looks like it's involved in concentration. Well, except for voltage, of course. So the gas constant, this energy temperature per mole, so that's concentration. Temperature is also going to affect the movement across the membrane down a concentration gradient too, and we even have temperature associated with this, so we know that's involved in concentration. And of course, voltage is an electrical force. So again, this is where electrical forces are equal and opposite to the concentration forces or the chemical forces. So I can show you how that would play out. We can rearrange this simple formula here so that we have, it'd be ZF voltage. I'm just going to do the E ion, so you know what we're dealing with here. This is multiplied times the natural log of our concentration gradient again. And I'm going to get it shorter because this is taking a while. So again, this is electromotive force here, electrical force. And again, we can consider that electromotive force compared to concentration. And I just showed you this to prove to you that what the formula is doing is setting electrical forces equal and essentially opposite to the concentration. And that's how we're going to reach electrochemical equilibrium. And let me just do one more thing for you here. I'm going to simplify this quite a lot, actually. Let me get a little, this pen's a little hard to read sometimes. So if we plug in the constants, we can assume our temperature is at body temperature. We can put that at like 37 degrees C, which is about, I think, 310 or so in degrees Kelvin. We can convert that to a log base 10. Those are easier to work with too. I think we multiply that times 2.3 to get that done. But I'm just going to do that for you. And we're going to simplify this, and we're going to be doing our calculations when we're at 37 degrees C. So that complicated formula I gave you, yeah, you don't have to memorize that. Let me give you the easy one. So for Nernst, let's just do this. We'll take the voltage. Again, it's going to be our, I'll put the little E down here to tell us this is the voltage at equilibrium of the ion. That's going to be equal to minus 61.5. That's from plugging our constants in there, over Z. We do have to keep that because sometimes we're dealing with positive ions, other times negative. But if you think about it, it's always going to be 1. This is only for monovalent ions. So if this is a 1, well, that fraction just drops out, right? We just have minus 61.5. If it's minus 1, same thing happens. We just lose the minus sign. Yeah, pretty easy. And again, this is going to be times now. We're dealing with a log base 10. Much easier taking the log of this ratio over here. Ion concentration. We have to keep our concentration gradient in here. On the outside. And let me just show you how I calculated that minus 61.5, looking familiar, millivolt difference across the beaker with those ion concentrations we had across the membrane that was only permeable to potassium. So go back down, get a little bit of lag here. Let me show you how I did that. I'm going to go to it. So we want to know this is the voltage that we see once we have equilibrium. So now it's potassium. So I can just put a little K down here instead of saying ion. Well, that's equal to minus 61.5 over 1 because this is a positively charged ion, so it's just plus 1. So I'm just actually going to do that right off the bat here and just say minus 61.5 times the log of this ratio. Here's the ratio I've got here. So ion on the inside, we had 100 millimolar. And I don't have to put the units on that as long as we're dealing with the same units across, and I'm going to shorten that to just N. So that's on the inside, really on the left side of our beaker. So I could put left there, it'd be fine. And it was 10 on the other side, 10 millimolar. Again, we could also say left and right here for this. So the math here is actually quite simple. First thing you do is you take this ratio, well, 100 over 10, that's pretty straightforward, isn't it? So 100 over 10, that actually is just going to go to 10 over 1, which is just 10. Log of 10 equals 1. 1 times minus 61.5, aha, there's my answer. So once we get a voltage across the membrane of minus 61.5 millivolts, again, based on the way we set this up, well, then we're in equilibrium. No more ions are moving across the membrane. And that's enough for now. We'll start looking at some real membranes